In the Netherlands, there's an ambitious company that built one of the most advanced and expensive tools in the world. A single unit costs hundreds of millions of dollars. And when companies buy one, they also need 250 engineers to install the 165-ton device to process that typically takes half a year. But despite this steep cost in time and money, many microchip makers desperately want one of these machines. The $100 million question is why? The answer has to do with something called Moore's Law, the first coined by Intel co-founder Gordon Moore. This law states that every 1 to 2 years, the number of transistors that can fit on a given size computing chip will double, and by extension, the rough number of calculations the chip can do per second will also double. Now, this law isn't a physical law like gravity. It's just a trend Moore observed during the early 1960s, but chip making turned the trend into goal. And in turn, consumers learn to expect computing progress to continue at this exponentially fast pace. And the amazing thing is, for 6 decades, it pretty much has. Thanks to Moore's law, chips have gotten smaller, faster, and more efficient, and cheaper. But today, there are 4 key problems that trip up this trend, potentially ending Moore's law and fundamentally changing how we make progress in computing. The first is the transistor size. Transistors are basically on and off switches, and these building blocks of digital computing have been shrinking since the 1960s, but recently they've gotten so small. Quantum physics has begun to interfere with their functions. When a transistor switch or gate is less than 20 nanometers, electron will turn on it continuously, turning a crisp on and off switch into a hazy dimmer. The second problem is heat. As chip makers make components smaller and more complex, the copper line that runs between them need to be thinner and longer. This increases their electrical resistance and generates high heat that impair the chip performance and can't be easily dissipated. Today's chip can only run hot enough to cook an egg, and temperatures are only predicted to increase without new innovations. While both these issues represent limits in the fundamental physics of chip making, researchers haven't stopped trying to solve them. Unfortunately, their solution often exacerbates the third major problem, chip making the environmental impact. For example, swapping copper lines for lithium could help pack transistors more tightly and keep chips smaller. But the metal is far scarcer than copper and would require new mining infrastructure. Similarly, the technology currently used to make today's smallest transistors requires huge amount of energy and chemicals called phosphorus and polyfluorine substances, which can take thousands of years to break down in the environment. Managing these first 3 problems contribute to the final issue, cost. To keep achieving Moore's law, chip makers have to make individual chip components smaller. And this is where the costly $400 million machine comes in. This marvel of chip-making science shoots a stream of thin droplets into a vacuum chamber before blasting them with high-energy laser that vaporizes the tin to create plasma. In turn, the plasma emits a 30.5 nanometer wavelengths of ultraviolet light that can be used to produce incredibly small transistors. This remarkable feat of engineering has helped chip makers keep up with Moore's laws. But a chip keeps getting denser. Intricate manufacturing plants keep getting more expensive. These trends have been so consistent, it's actually earned the nickname of Moore's second law. Obviously, all these trajectories are unsustainable. Manufacturing plants can't keep increasing in price. Our ecosystem can't endure endless mining and pollution. The laws of physics are unlikely to change anytime soon. Fortunately, Moore's laws is flexible. There is no reason we can't introduce new laws. And there is no reason we can't introduce new goals to keep making computing progress responsibly. Perhaps we could introduce new sustainability law. Smaller transistors already use less material and produce less e-waste. Advancement in electronic photonic integration are allowing chips to use less energy and generate less heat. So perhaps chips should be made twice as sustainable every several years. Whatever the answer is, we make the laws. So the future is up to us.